default. Oh, which year is this? Okay, 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 that's fine. Okay, then what's the question? Uh, okay. Hmm. If there exists again k distinct. Okay, not equal to 1. Okay. Okay, 1 second. Okay. Hmm. Hmm. Right. Okay. Hmm. Hmm. Okay. This is equal to 1. Okay. Hmm. Hmm. Yeah. Yeah. Something. Okay. Okay. Is 4 stable? Hmm. 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 Maybe if k is stable, can you show that k plus 1 is stable or something like that? Yes. Yeah, gives. Yes, it will be like that only. This is not going to be harder than that. But exactly. Yes. Yeah, exactly. That's, I think, but let us just check the details. Yes. So you're saying multiply by 1 by 2. Yes, I think then it's done, right? These will be distinct. And you can share this is done. This is done. Yeah. So that's it. If k is stable, then k plus 1 is stable. Right. And yes, you can just do the same thing in general. Okay, this was easy. This was easy. Okay, easy. Yeah, yeah. So always you see something simple works. Always in these kind of problems. Okay, so basically, but we have proved something very interesting. We have proved that uh, that so basically we have proved that there are a lot of um, harmonic sums. So sum of reciprocals of integers, right? There are a large number of sum of reciprocals of integers which are integers, whose sum is integers. So right, so basically if I'm just saying that if you take the natural numbers and then if you construct this set H, which is summation 1 by ak, right, where k is natural, and obviously we are taking finite summations. Okay. Yes, then basically this set, I mean, obviously maybe we should not look at this as a set. Maybe we should look at it as a set and also remember the numbers where it is coming, which are being used, right? So we remember them, and so we take this tuple, right? Where we take this some subset of n, we take a subset of n, and then we do this addition, which is reciprocal, and we remember this whole information. Then this becomes 1, and hence it becomes natural numbers for for a large number of numbers, for a large number of tuples, right? Can you also show that if you replace this by n, means fixed n, that this is also true? They sum to n. They are all unequal to, yeah, here you are right. Whether I should put 1 or n, that's a good thing. Though I think it doesn't. Uh, mm, no, wait. So let us keep that to be 1 for the moment, and then can you do this? See, because the reason why, if that is 1, now if you are allowing 1, then basically the question becomes equivalent to n minus 1. Then so that's not any change in anything, right? So this is, yeah, because that 1 and that and distinct. Yes. So but so only one, right? That's why the question comes down to n minus 1 case. Right. You just cancel that and then the question comes down to this. Like if you allow 1, then it will come down to n minus 1, but you don't allow 1. So I won't allow 1 from the start. So that's not very interesting. So can you make this happen? Here what I'm trying to say is that it can be something like this. It can be that not all natural. So it's obviously 3 and 4 will not work. Small numbers will not work. Right. You understand, right? Like n equal to 3 will, sorry, k equal to 3 will not work. You can't get a huge number, but yes. But at some point, this harmonic sum will exceed n. That also you know. Mm-hmm. Huh? Yes, that's right, but what about things like this? So that's one of the problems. Yes. Let's think about this. These will all have nice answers. These questions are very patterned, right? This is yeah. So it may be something like that for any natural number n, there exists a k such that k is stable, k is n stable, and then maybe then k plus 1 may not be unstable, but there will be a period. K is stable, k plus n is stable, k plus 2n is stable, right? That's the correct generalization, because when you specialize it, you get this result of this problem, CMI problem. So there are two kinds of questions here. Means one is that is there a k for which it is stable? That is the first maybe one question that we can answer. Can you find? Huh. Okay. Huh. Hmm. No, the half will always remain, right? Yeah, that will not work. Yeah, at least in this method, the half will always remain. No, but you can still maybe make it work if you multiply with like 1 by 3, something like that, which is, yeah. Yeah, the problem is that for the case of 1, we don't have a rich class of representations. You understand what I'm saying, right? All our representations are sort of cheap. They are sort of built from the basic one. And that's why we cannot use them later. So the kind of lemma you would want to prove is the following, maybe. Maybe it's like this, is that for the case of 1, you should try to prove something like this. That So basically you want to build the n case from the one case, right? So maybe then one way is that you show something like this, okay, that any given any s, okay, there exists k such that this a1, a2, ak, they are all bigger than s, okay, and the summation 1 by AI is equal to 1. You see, so from any point onwards, you can create a case table. You can find numbers which will add up to 1. Yes, then you can, because then you can club them to create n, right? You can club this rich class of representations. Yes, then you can club them, right? But even that method of clubbing is not very nice, because it's sort of, but it's better than using these copies of one. Yeah. But and also why this, why well, there's one reason to believe why this is true is the following, and I don't know if you know this, that, and this is a very good result in like calculus. You can prove this. So let's say that, okay, let's say that you give me a number m. Okay. So, and you can also try to prove this result. This is a very useful one. Given number m, okay, there exists, maybe I will not use this thing. There exists m1 and m2 such that, look at this summation. Look at this summation. And this n, this is bigger than m. Yeah, you know this? Uh, yes, but then yeah, that is the point. Yes, the harmonic series diverging, it basically means this. Those were actually the same things. For any series that diverges, basically any point you go, any point, no matter how far you are from one, you can still add up and create large quantities. And any large. And so that's why basically you can also make this bigger than one, it means, right? So it means that you can exceed one, at least numerically. But can you become equal to one? That's a question. That is a question we are asking, right? Given any, right? Given any, yes. Oh, no, no, no. Wait. What am I saying? Yeah, I should actually say like this: S. There exists M1 and M2 bigger than S. Right, that is what we want to say. Otherwise, it's a trivial fact. You can just start with M1 equal to 1. Then and that is the same thing as harmonic series diverges. Yes, S is given to you. So no matter how large you, because see, I'll tell you what, see, harmonic series diverges, right? So if you start from 1, then you can add sufficient number of terms and become bigger than anything, right? But then if you start with S, then you forget the first S terms of the harmonic series, the resulting series still diverges. How will it converge, right? Otherwise, you can just add finitely many. So then basically you can play the same game from S onwards. Right. And so again, it becomes bigger than M. So basically this, and that's why there's numerical confirmation for this. But now this is also, the integers have to add up. So this one you can, yeah, this one is actually proved. So this is basically called the Cauchy criteria for convergence. Right. Yeah. So yeah, so this one, yeah, just think about this one also. Let's see. Yeah, maybe if you can prove this, or if you can just prove this directly. Right. And then maybe try to prove that there are at least one stable number, and then maybe try to prove that there are infinitely many stable numbers. Right. Those two are the. No, sorry. I did not mean to say like that. I'm sorry. Yeah. What I tried to show is that what I tried to say is that n is a stable number. Sorry, sorry. What I'm trying to say is that n, prove that every number n has a representation like this. Okay, and for every number n, there are infinitely many such representations. Oh, right, infinitely many case for which that n can be written. Right? So those are the two things. Yeah, think about that. Yes, and the reason why I was saying that is because what is looking here like is the following. For example, at least when we had one, at least in that case, it's confirmed. Like one can be written in this way in many, many ways. And for every k, you can sort of write it apart from 1, 2, 3, first few. 1 and 2. So that's right. But if you, so that's the problem when you start with an integer and you see how many ways, I mean, whether it can be written as 1 by something. Okay, and the answer seems to be yes. But there are a whole class of problems in the other direction, which you can again try out. Is that if you start with, just forget these things and just start with the other end, right? Just start with an expression like this. Okay, and then ask, how often is this an integer? Okay, yes, sort of the reverse question, yeah. And then along that lines, you can certainly prove the following, that hn is not an integer, or not even that, just the expression I wrote, that is actually never an integer. This is never an integer. Yes, so you know this. Okay, then that's good. And along these lines, there will be other statements also. Okay, that 1 by n's are never integers. Like suppose 1 by ni, this thing will never be integer I from 1 to k when if ni's have certain features. Okay, for example, if there is a prime which divides all of them but doesn't divide one of them, then this will again not be an integer, something like that. Okay, but it will be similar to that, taking LCM, and if you know that proof, if you know that proof, then you know. So these are actually big questions. How often is this thing an integer? So yeah, this is it. Then let me just mention that Cauchy criteria thing. You can go back and read it, but let me just mention because it's very useful. So uh, yeah, let us start with the most basic thing. So you know what it means for a sequence to converge, right? So yeah, so this thing, let's say that this thing converges to some number L. So this is something that you know. So everything is in reals, and this sequence converges. Now, uh, yeah, this implies that, and this is easy to prove. This implies that. So I'm not writing the definition, but similar to that. Given epsilon greater than 0, there exists a n such that for all n1, n2 bigger than n, a of n1 minus a of n2 is less than epsilon. Yeah, so this is okay. If can you prove this from the actual limit definition, which is the actual no, this is delta or n naught. This is a limit of sequences. This is not a limit of function. Yeah, so that's okay. So this is a limit of sequences. So what does this mean? You can just recall that quickly. It just means that given epsilon greater than 0, there exists a n such that, or rather there exists a n naught such that for all n bigger than n naught, basically this sequence comes close to this L. This is the definition, right? From here, can you prove this? Right? This is a very useful criteria because whenever you mean, it's like kind of stating the definition of limit of a sequence without referring to the limit constructively. You see, right? If this implication, right, in the second statement, you see there is no, the limit just vanishes. Right? So, yes. So, okay, and the sequence. Can you prove this just? Yes. This is the easy direction. The reverse is the actual useful one. Okay, which we will come to. Okay, try to draw some pictures because this is easy. So yeah, so let us see. Let's try to draw. Maybe you don't usually draw pictures for sequences, but you can draw them, right? So for one, let's say first we mark the input. Sequence is just a function, but the input is integers, and there is no sort of, there is no metric, there is no distance on the range space kind of. Okay, right? Yeah. So this is like that. It goes, and then the limit is L, right? And then we have this epsilon. I'm just first writing the definition. Okay. Or let me not write the definition. Let me just go for what we want to prove. Okay. So what we want to prove is that given this epsilon, right, we want to say that all the terms of the sequence become epsilon close to each other after some n, right? You have to translate this in words, at least in the beginning, till you are very comfortable with it, right? Because even whenever we learn something new, we have to translate it in what we already know. So just right now, we just maybe know English, so we sort of translate it into that. They get arbitrary close after certain n. That's what you want to show, right? So arbitrary close to what? I mean, what's the holding line? That is the line y equal to L. That's the attractor. That's the attracting line, right? So then that's it, right? So basically this line L, and then you know that there is a n naught. You will use that. There is a n naught such that all the terms of the sequence. So let me just, this is A1, this is A2, this is A3, this is A4, A5. But all the terms of the sequence are in this after n naught, right? After n naught onwards. But what does this mean? It means that for example, a n naught plus 1 minus a n naught plus 2, what is the distance? What can be the maximum distance? Less than 2 epsilon. Exactly, right. That's it. And then you are done, right? So what you have to just do is you have to take epsilon by 2 here because you are allowed for all, right? I mean, right. So you just take epsilon, then you get epsilon. Right? So yeah, given any n for all n1 and n2, no matter how large they are, right? This happens, right? This is sort of, as you said, it's just the definition. Basically, from the definition of limit of sequence, without using any more calculus, but just using the logical symbol manipulation, we get this, right? There is nothing. This was just an assistance, right? But uh, but the main thing is not that. The main thing, because see, this will just give you something. If the limit is given to exist, then it will give you something, right? Or maybe, or it can help you to show that limit does not exist. You see, like imagine where can this be used in what kind of problems? If you're looking from that perspective, this can help you to prove when limit of a sequence does not exist. Yes, right. Because if this condition does not hold, then certainly the limit will not exist. The contrapositive, if you want to use the word. But we want to prove the other direction. That is the real thing. That will help you to prove that limit exists. Because you see, without actually finding the limit, that's because a lot of times the limit point is not easily describable in the language that the question is given. Non-constructive, right? So let's try to go from here to there. This maybe you cannot do on your own. If you have never done this kind of thing, maybe it's a little tricky. But so let us do this together, and then when you see what is the key ingredient, then you can do it. So yes, so let us see. So we want to show this. We want to show that this right. So, well, the first thing is that you can show from here. This implies that a wait, no, sorry. Yeah, that's right. This implies that an I'll use this to denote the sequence. Okay. When I write that, it means that I'm talking about the entire sequence and not any term, right? I mean, it's better to write maybe 1 to infinity. So this entire symbol stands for sequence, the sequence, not any particular term. This means that this condition at least means that this is bounded, right? You see, why I'm doing all this, when I do it, you will see it. That's why I'm not elaborating it, okay? Because you will be able to see it. But you see, it certainly implies that the sequence is bounded, right? Right, because why not? I mean, just take epsilon equal to 1, right? And it just means that an minus an plus 1, but you can do it in any way, is less than 1. So certainly an plus 1 is less than 1 plus an, right? And so this is sort of a fixed thing, and before an whatever finitely many terms are there, you can take care of. So it's bounded, that you can prove, you can sit and prove that properly, write it out. So we should write these things out in this stage. But okay, it is bounded. Okay, now what is the key? I mean, now the thing is that if you have a bounded sequence, then it always has a convergent subsequence, right? Yes, this is something which you may not know, right? Yes, yes, yeah. So see, let's try to look at the picture. So this is, what is this saying? This is just saying that the terms of the sequence come arbitrarily close, right? Okay, but why should this imply that they become arbitrarily close to a fixed number? Yes, yes, yeah, but boundedness is sort of a very weak thing, right? Actually, this is much more than just bounded, right? This is just saying that this is this is sort of saying that given any epsilon band, right? Um, yeah, given any epsilon band, all the terms of the sequence are inside it after a certain time. Right. So for example, given any epsilon band, you can find a n, and then वो an का epsilon band में everything is there, right? From this given condition. But then the problem is uh, that when you, so this obviously you can all, so this implies that it is bounded. Okay. Yeah. Uh, But so does this tell you that there will be a certain L to which they will all move? It kind of tells, but I mean, yes, 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 right. So then exactly right. So if you take this n, then you have this epsilon band in which they are all in, and then you can make this epsilon band sort of smaller, right? So you can make epsilon by 2, right? When you make epsilon by 2, then you will get a sub band. That's the more important thing, not just that any small epsilon band anywhere on the y-axis, right? But it will be inside this band. You can find it inside this band only, right? Because all the terms are inside this band, right? That's the good thing, that you can find it inside this band, and then you can find another one inside this band, and so on, right? So if from here, if the limit did not exist, then that would speak of the deficiency of availability of numbers in the real line. You see, right? Because it means that these things are going somewhere. But then if L does not, if they did not, then it would mean that the real numbers lack numbers. You see, that is the thing, and that is the thing. What I'm trying to say is that once when we prove this, you will see that this can be used to actually define the real numbers. Okay, this can be used to actually define the real. Yes, Cauchy sequences sort of, yeah. So basically you take Q, you take the rational numbers, and then you take a set that is containing it. Okay. And if it is the smallest set containing Q, where this thing implies that limit exists, then that set is the real numbers. Okay. Yes, I mean, obviously, I have to say more things. There are a few more things. It's not so, yeah, vague, but that's what roughly the idea is. So basically, the real numbers, the rational numbers don't have this property because some numbers should be there, but it is not there. Okay, then we add some numbers, and what numbers do we add? We add the numbers which are supposed to be the limits of these sequences. So you take the rational numbers and you take nice sequences like this in the rational numbers, okay, which are nice in this second sense, that they are Cauchy. This, You take this, so you start with the rational numbers and you take these kind of sequences, okay? And then you realize that they don't converge. Some of them don't converge because you're in Q, right? So for every sequence, you designate a number. You declare a new number, okay, which will be the limit of that sequence. Okay, and that collection you form and you say that is my new the set, and that set turns out, that set we define to be R. Okay, and and then some other mathematicians construct R in some different way, and then it turns out that they are some they are same. Okay, so basically this is very, very fundamental. Okay, so yes. So now let us just finish the argument. Yes. Okay. Now, by the way, the reason why I started to draw the picture is the following, because you see, as you understand that this sequence should converge, the only problem is that maybe the real numbers don't have enough numbers. Okay. What that just means is that if I can find a subsequence that converges. Okay. So if I can find a subsequence, which means that, some n1, some n2, not consecutive terms. Okay. And along this subsequence, if the terms converge to some L, okay, right? So what I'm just trying to say is that if there is a subsequence, if there exists, so you understand subsequence, right? Yes, terms of, if there is this subsequence that converges to some L, then the whole sequence must converge to that L. Because of that condition, they are all close. That you can prove. That is where they use the condition, right? Exactly. So that you can prove, that implies that the whole sequence converges. Now, why is there a subsequence why is there a subsequence that converges? That's the question, right? And that is because it is bounded. So then everything comes down to this thing, that every bounded sequence has a convergent subsequence, right? So bounded implies that there exists a convergent subsequence. Okay. Yeah. And yeah, that's it. If you assume that, if you're willing to assume that, then there is nothing after that. Okay. Now, why a bounded sequence has a convergence subsequence is also an easy fact, but I will leave it to you to just discover. Yeah. Yeah. You can think. Huh. Yes, exactly. It is just that same thing, that yeah, you have a bounded space, right? So you can keep dividing it, dividing it, dividing it, dividing it. Then there is and they should go there. Yeah, but yeah, you will think about it. Yeah, and the way typically it is proved is the following, right? You have a bounded sequence, you show that it has a monotonic subsequence. Okay, and that is a completely combinatorics fact. That any sequence, so you know that Erdos-Sizek's lemma or something, right? That if you have a sequence of n square plus one terms, then there are n plus one terms which are either increasing or decreasing. Might have heard of it, right? This is just that. This is just that for the infinite case. Think about it, right? So you prove that, then it cannot happen that you cannot prove this. I mean, the proof is this will be the same, right? In fact, that is a harder statement. That combinatorics problem is harder. That in n square plus one, you get n plus one which are increasing. Right. Yeah, so you prove that, and that's a standard question, standard combinatorics question, right? It's something that you should know, you should be able to prove. So you prove that, then you can prove this, and then you have a monotonic sequence. Now if you take a monotonic sequence which is bounded, it will converge. Where will it converge? To its supremum, to its least upper bound, right? Why does it exist? By definition, because real numbers have the least upper bound. I mean, the model of real numbers usually we take is that it has the least upper bound property, that every set has a, so every set may not have a maximum, but its collection of upper bounds has a minimum. Right, that's the least upper bound or supremum, or any number of words, other related, right? And that's key. So from there you can come here, and you can prove from here to there also, but anyways, we'll, yeah. So that's the story. Now basically how this is used in the theory of the theory of series, right? What does it mean for the theory of series, right? So suppose that we have a series that is, we'll just quickly define this series, and suppose that this is convergent, right? What does this mean? Well, this infinite sum has no meaning. So what does this mean? Well, this means that if you take the partial sums, right? So you understand this, yeah? They converge. That's the only reasonable meaning you can, because you want to say this in terms of convergence of sequences, and the sequence you make is a sequence of partial sums, right? This converges. This converges, right? And from what we have seen, this implies that this sequence is Cauchy. What that means is that definition. It means that it means that given any epsilon greater than 0, there exists a n such that there is n such that Sn1 minus Sn2, this is less than epsilon for all n1 and n2 bigger than n. That and the reverse relation is also true. That was the hard part which we were just discussing, right? So it's if and only if. But then what does this mean? This is basically the terms from n1, sorry, whatever, if suppose n1 is bigger than n2 or n2 is bigger than n1, that's how it should be. Then it just means that you're just summing up the terms from n1 plus 1 up to an2, right? That is what this difference is, right? First n1 terms gone, and this is less than epsilon, right? That is what it means. Just the definition, right? So, but this looks a little different, right? I mean, it's the same thing, but once you see it, but it's a nice criteria, right? Now, what does this mean? Now, this is true for all n1 and n2. Well, this also means that you can exactly, and a little more than that, which is the same thing, but you can make the sum from n1 onwards as small as that, no matter whatever n2 is, which is basically in the statement, right? And that means that you can make this sum, this limit, less than equal to epsilon, because that's what it means, right? Because basically if you consider this as your new sequence, right, sort of cut this, suppose you call this is starting from s1, right? And then s2 would be when it ends at n2 plus 1, and so on, right? So if you take s1 prime to be uh, from here up to an2, okay, and then s1 s2 prime to be an2 plus an2 plus 1, and so on. It means that this sequence, yeah, this sequence, it is less than epsilon always, right? So wherever it converges, it will be less than epsilon, right? Limit cannot be more than the terms. Every term is less than epsilon, right? So this means that this infinite sum is less than epsilon, because that infinite sum is the limit. And that is basically that the tail. So you can basically, given any epsilon, that you can go to a term so that beyond that term, when you add, that is 0, right? So basically, I mean, the fact that we know that if your sequence converges and the terms go to 0, that everybody knows, right? Terms have to go to 0. You can prove it. If you have not proved it, you should prove that if a sequence converges, the terms go to 0. But here we are saying much more than that. That not just the term, the tail must go to 0. Right, the tail must go to 0. The tail must go to 0, and you can see you can see it very concretely. For example, in the geometric progression. So suppose you have the geometric progression and you start with k, and you add them, right? You see, you can make this as small as you want, because what is this summation? This summation is 1 by 2 to the power k times half or something, or maybe it is just 1 by 2 to the power k, or whatever. I mean, maybe k minus 1 or something. Yeah, just something like that. Basically, this tail is you can make, and that you can make as small as you want if you're willing to change the k, increase the k, right? So the tail can be made as small as you want. Okay, and if it doesn't converge, then the tail can be made as large as you want. Or I mean, no. So maybe that. Sorry. No, the tail. No, not as large as you want, but no. Is that? Yeah, the tail can be. Mm, no. So let us just look at that. Let's go back. Uh, Yes. Yeah. Then I mean, but let us. Oh, 1 second. No, so the tail can be made as large as you want. That's not correct, right? Uh, because see, I will because yeah. So that's a small thing. That's a subtle thing, small one. So for example, if you have this sequence, I mean, so actually the definition doesn't tell you that the tail can be made as large as you want, right? So for example, if you're starting with this one, right? If you're starting with this one, then this implies convergence, right? And convergence implies this, right? So yeah. So if this series is not convergent, what does that mean? It means that there will be some epsilon such that you will fail to do this, right? Which means that this will be bigger than epsilon, right? So no matter what you take, there will be a point where it becomes bigger than epsilon, right? But that doesn't mean it will be bigger than any number, right? Yeah, just that bigger than epsilon. And you can see this in this kind of whatever, yeah, in this kind of sequence. I mean, right? I mean, the tail cannot be made more than one, but it cannot be made as small as you want either, right? And so that's yeah, yeah. Then you can use that to prove it doesn't converge, or you can say it on your own that it doesn't converge, right? Right. But then let us just finish this sequence of the comments with this small thing. Uh, let us finish this sequence of comments with the small things, which I suppose is true. And here this is. So suppose that all the AIs are, so this is the last thing we are saying in this, okay, for today. Suppose that the AIs are positive. All the AIs are positive, okay. And now you say that this sum diverges, okay. So from here, it means that, and this is actually a trivial thing now. Okay, this actually I already said, sorry. But let's see this in a clean way, okay, because without any hn and without any 1 by n. So this series diverges. It means that given any m and s, there exists a n1 such that a n1, a n2, this I mean this can be made bigger than m. It will, yes, it will. Sorry. Yeah, right. I mean, I should just say that it is bigger than S. N1 is bigger than S. Yeah, or actually, not is unnecessary. So I'll just say AS, AS plus one. Yeah, I mean, there's no need to say that they're existing, right? It's just yeah. This has captures the idea. Yes, then this is trivial because of positivity, right? So basically, for positive sequences, not converging does not just imply that the tail can be made bigger than some epsilon, but implies that tail can be made infinity, which is an obvious statement. Right? So so that's why when you study the theory of series, you will see that the theory of positive series is different. At some stage, it becomes different, and the theory of random series becomes slightly different. Obviously, they interact, but yeah, things are not the same. All right. So yeah. So let's see. Do you have any more questions? Then huh? Okay. 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 So 100 light bulbs in a horizontal row. Okay. Okay. Mm-hmm. Okay. Person one. switches every ball on. Okay. Switches off every second bulb, starting with one or okay, okay. Switches off two or okay. Mm-hmm. Okay, okay, I understand. Okay. Uh-huh. Okay. Hmm. Okay. How is it some LCM business? Yeah, yeah, I get that. I get that. I get that. Yeah. Yeah. Okay. Yeah, so these are perfect squares. These are the perfect squares. Yeah. Okay. Huh. Uh-huh. Mm-hmm. Uh-huh. Mm-hmm. Okay. Okay. Oh no, that function will be very difficult. That function will not have any uh, number of divisors of. But let's look at. No, no, no. That kind of thing cannot be studied, I think, because you see, you don't know the prime factors of n, right? Which numbers that I. You can give some bounds, yeah. Number of divisors of. Uh, yes, yes, yeah, yes, yes, yeah. That is right. Okay, so but can you say your answer in terms of FM? Let's say that FMN is, let's say we assume that, then what will be the number of bulbs in terms of FMN? Number of bulbs switched on in terms of F. Huh? Huh? Okay, yeah, I mean, if yes, yeah, so it will be right, right, correct, correct. So that will be some, no, that will be some crazy thing, right? Yeah, if you think if the number of people is large. Oh, yes, yes, yeah, that's right. Then the answer doesn't change, right? Yeah. But the function doesn't really help give you any insight. It helps you to, but yeah, it might in a certain, yeah. So the question is coming down to uh, given m and n, how many? No, so it is you don't actually need to know f of mn, right? You need to know this summation f of m comma n mod 2. Right, you need to know this summation where okay, maybe not n because that n is the number of bulbs, so it should be k, right? Uh, K from one, and you need to know this thing. So basically, this may have a nice answer. I don't know. I don't know. That doesn't mean it doesn't have. Right? So K, yeah. So yeah. I mean, so again, just like you said, right? You can focus on K bigger than M, because below that it is just a number of perfect squares. Right. You see, so that has a nice answer. Uh, yes, yes, right? Yeah. But then after that, after that it will become really crazy. It depends on the prime factors and their size and so on. Yes. So I mean, it is hard, definitely, but is there anything interesting in it that I don't know? I don't see. I mean, is there any interesting version of the question, right, which can be approached? That I am not. I don't know. Huh? Yes. Huh. Okay. Uh-huh. Right. Right. But so what are you expecting here, f of f, this summation to be? You want to put some like bounds or something, some bound. No, no, mod 2 is not on the entire summation. That will be wrong if I write that. That will be wrong. Yeah. Mod 2, because you understand. I mean, you said right. F of m comma k. You want to know the parity of that. If that is odd, then that bulb will be on. Right. That's why I wrote that. Mod 2 is not on the summation. This gives us the number of bulbs that are on. Right. When you introduce this function, this nice function, then we get this. Right. But yeah. So basically, you're looking at number of yeah, number of divisors of n which are less than m, and if that number is less than equal to m, and if that number is odd. Right, right. So yeah, that might have something nice. I don't know. Means nice in the sense that you would want to be able to give some bound, like let's say it is m n by m or something. Like yeah, something like maybe a root of n by m. Because see, here the answer was root n, right? So is the answer n, is it less than that? Something, exact answer may not exist, but something like this can exist. But so yeah, I mean, you can certainly give some bound. For example, if you assume that n is 2 to the power k, then you can sort of say how many means right, how many divisors are less than m in terms of log 2 something. Right, then you can give that bound, and that bound may be the upper bound when the number has more divisors, or it will be lower bound or something, right? Or you can take the other extreme case. No, forget the other extreme case, will be very difficult. Then means that it has all distinct prime factors, right? But then the product of those distinct prime factors, I don't think you can work with that. Uh, yeah, yeah. But my point is that one bound can be gotten by taking n equal to 2 to the power k. Okay. With that, you can certainly say how many divisors are there less than equal to m. You can give a bound on that in terms of log, right? And then maybe you will have something to say in that case. But again, it's also about even and odd. So I don't know. Yeah, it's been become very, very, yeah. I don't know where it goes. Yeah. Okay. Uh, yeah. So do you have any questions? I wanted to share one question with you. Yeah. Yes. So just I'll just give you a outline and then you can try work on it. Okay. And through that, you learn a few things hopefully. So yeah. So what are we trying to do? What are we trying to say? So first I will need two things, and that is holders inequality. I'll state them if you don't know. Maybe holders will not be needed, but holders inequality. If you don't know, then just look at this. Okay. But the one that I will state, which is sort of I think will be useful, is Minkowski's inequality. Okay. Now obviously these are people say these are advanced inequalities, and that they are advanced, but they also have some nice meaning. Okay. And you don't have to always use them in that way and so on, in the complete generality. So what is Minkowski's inequality? What is Minkowski's inequality? Right. So well, the point is that it starts with a triangle inequality, right? So if you start with the triangle inequality, then what does it say? It says that given any two numbers, this is less than right. Yeah. So now we want to say that this is obviously true, not just here, but it is true for any distance, right? Whenever there is a sense of distance between points, right? So if x and y are points in space, then this will be true, right? Maybe you will be, this is more related if you write like this, right? If distance between x and y is less than the other two sides. So basically any sense of distance that you can introduce, this will be true, okay? So now let us say that you are working in R2, right? Then you understand the R2 distance, right? Distance, so x. So I will write x vector. You understand that, right? So x vector, y, and this just means that the R2 distance, which means the sum of the squares, square root of that, and so on, right? Uh, yeah, even in complex numbers, same thing, right? So this is just going to be x1 minus x2 square plus y1 minus y2 square, right? So this is a shorthand for that, and it's a nice shorthand. It looks nice. So it is this, and then you obviously also know this, and you can just prove it. But then, I mean, but for the reasons why this is true, I mean, so it is true because it's in the plane. But when you try to write a proof, you will see that the number of terms being two doesn't really matter. This will be true in any. Right. I mean, but the proof is just induction or something, or you can Cauchy-Schwarz or induction mixture of those things, right? It should come. You can prove it, right? Just by in the worst case, just square it and check it, right? Square both sides and check it, right? So this will be true. And now you understand what this means, where these things are living, right? X is a tuple of n tuple of numbers, y is an n tuple of numbers, right? And again, root sum of squares. In a Olympiad question, it won't be written like this. It will be written as root sum of squares and so on, but it is this only, right? Okay. So, so there is one change we made, that is the change in the dimensions, right? But now I'm going to make another change, and that is the change in the sense of distance. Change in the sense of distance. So when you're in R2, so there are two kinds of changes going on, and we have to take both, because finally the question that will be matrix question, it will be based on need both. So in R2, when you write distance of right, when you write mod x, and you're just looking at this distance, right? X1 square plus x2 square, square root of that, right? This. But then I may also introduce a different sense of distance, where I will say that distance between 0 and x is this length plus this length. I can declare that to be the distance. A different metric, exactly. That's called the taxi cab distance, right? When you're parking lot, then you cannot really just run through the cars, right? You have to or something, maybe Manhattan. Okay, streets. Yeah, streets. Yeah, that's right. Yeah, that's right. Yeah. So this kind of thing. But then in the terms of coordinates, this distance. So this is now the original distance. Now we have two distances, so we need different notations, right? So this original distance, I will now put 2, and you understand why. The formula, right? Formula had the squares, right? So we put 2, right? And now I will have this other distance, which will be 1, which is this taxi cab distance. And what is that? Yeah, it no squares involved, and it will just be like this. The no, I mean x2, right? Xn. I mean for this, and y similarly for y. I mean this is a vector, so this will be x1 minus yn mod plus x2 minus y2 mod plus x3 minus y3 mod, like that, right? So now we have many kinds of distances. But then, so basically this is the one version of that. Basically there is a root, but it is 1th root, and so you don't write it. Okay. Yeah, right. And that motivates us to any p. Okay. And what is that? That is just then the distance will become raise it to the power p, take the p. Exactly. Okay. So we have all kinds of distances, and the inequalities still stand. Inequality, yeah, for that notion of distance is still, but obviously you have to prove it, right? Now it is something that should be true, right? But you have to prove it. Okay. So it turns out that when p is bigger than equal to 1, it is true. P less than equal to 1, it is not true actually. Okay. For p bigger than equal to 1, it is true. And then it has become proved. This is actually called the Minkowski's inequality. So Minkowski's inequality is just a triangle inequality. Okay. So that's what it means. Okay. Now I want you to prove something. So now I want you to take this problem and think about it. You can think about it in the R2 case, two-dimensional case, but I will state it in a general case. So suppose that A is a n by n matrix. I mean, you should do it in the R2 case, but I will state it in this case. This thing and is invertible. Okay. Is invertible. Now, suppose that for all x in Rn, I mean this is a vector Ax. So Ax is in Rn, right? Here you take the qth distance to understand that, and on the input you take the pth distance, and if this happens, okay, so basically in the input space, whatever the distance was, in the output space, whatever its notion of distance is, the distance is same numerically, right? Yeah, so for example, if you take the identity function and if you take the normal distance, then this is true, right? I mean, distance of input is same as distance of output because the input and output are same, right? Right. But here, if you take identity, it will not work because input may you're taking pth distance and output may you're taking a different distance. So the same vector will not have will not have two different distances. So it doesn't work. But then we are saying that it never works. So we are trying to show that if this is true, then prove p equal to q. Yeah. So you cannot do it with any matrix. Okay. So yeah, try to prove this for 2 by 2 case and see what you can do. It will basically become an inequality problem, Olympiad inequality problem. Okay, but I'm just writing it in a geometric way, whatever. Okay. So yes, so try this for you see for n equal to 1 case. But okay, sorry, I should say here that n is bigger than 1. In n equal to 1 case, this is true. Yeah, because see, if n is equal to 1, then those two distances become same, right? Because you have to take a number, raise it to pth root, and then raise it to pth power, and then take the pth root. I mean, you have to take the mod. So in the definition, I was taking mod every time. You should remember that. Okay. So take the mod and then raise it to pth root, pth power, and then take pth root. And then take the mod, take the qth power, qth root. Obviously, these are same. If it is just a number, so in R it's nothing, but in n bigger than 1, these are the things happen. Okay. Yeah. So basically, we're saying that if p is not equal to q, then there is no function. A is like a function, right? There is no function which takes this notion of distance to that notion of distance. It's something like that. Yeah. Okay. So then we will stop here, and maybe if you free, then we can tomorrow, if because you have exams, so you can think about it and then tell me. Okay. Okay. Then it is fine. Yeah, but do keep in touch with the practice. Okay, so yeah, okay, okay, then take care.